Hi guys, today we will cover the next section, that is axial load. And firstly you need to be familiar with St Venant's principle. That is a fundamental concept in the strength of materials that helps simplify the analysis of stress and strain in engineering structures. So if you have, for instance, some column subjected to some force, and we have a different cross sections, for instance AA, BB, and CC, you will see that load distorts lines are located near load, but lines located away from the load and support remain straight. So St Venant's principle states that the difference between the effects of two different but statically equivalent loads becomes very small at sufficiently large distances from the load application area. If two different loading conditions produce the same result on force and moment, then away from the region where the loads are applied, the resulting stress and strain fields will be nearly identical. So this will give you opportunity to ignore the exact details of load application, to focus on stress and strain far from the loading region, and to use simplified or idealized load models. If we have, for instance, a beam or column subjected to one force at the end, that is one case, and on the other hand we have a column which is subjected to two forces, the result will be near the application point, the stress distribution will be different, but a few blocks or widths away, the stress becomes nearly the same in both cases. So when we have axial load, we are talking firstly about elastic deformation, and this phenomenon occurs when a material returns to its original shape after the applied axial load, tensile or compressive, is removed. It obeys Hooke's law, and deformation is linear and reversible within the elastic limit. When I was talking about stress sigma epsilon diagram or stress strain diagram, I said that the straight line is our elastic region, and that is the only region where Hooke's law is applicable, which means that stress is equal modulus of elasticity times strain. So for axially loaded member, an axially loaded member is a structural element like a rod, bar, or column that experiences a force along its longitudinal axis. There are two types of loads. We have a tension or pulling apart, and compression when we are talking pushing together. So if we have tension or compression force at the end of the column or a rod, elastic deformation here will be delta L is equal P times L over A times E, where P is axial load or force, tension plus compression minus. L is original length of the member, then we have A as a cross-sectional area, and we have Young's modulus of elasticity for E. So now delta L will be change in length or deformation. So firstly, we are talking about some assumptions which we used. Material is homogeneous and isotropic. Load is static and centrally applied. Member remains within elastic limits, so we are not going into plasticity. We don't have buckling. That means that we have enough thickness for our member which is subjected to compression force. And we have, for instance, uniform cross section. In the first case where we have uniform cross section, our delta will be force N or P times length over cross sectional area times modulus of elasticity. If we have, for instance, the second case which is given in your figure B, we have two different cross sectional areas, and we have some different forces P1, P2, P3, P4. What we have to do, we need to cut and to find internal forces. For instance, firstly, we need to find internal forces in the middle of a length L1. Then we have to find the internal forces in the middle of length L2. We have L3, L4, etc. So our delta, or delta L, will be summation of all these forces times length over modulus of elasticity times cross-sectional area. Here we have one example. We have the copper shaft, which is subjected to the axial loads shown here, and we need to determine the displacement of end A with respect to end B. The diameters of each segment are between A and B 3 inch, between B and C we have 2 inch, between C and D is 1, and we are taking here modulus of elasticity to be 18,000 ksi. So in the segment AB we have 6 kips force, that is our internal force, which is pulling. That means it is a positive. Firstly, we need to find also area for each segment. For this segment AB, we have diameter on square times pi over 4, which is 3 on square times pi over 4. That will give me 2.25 times pi inch on square. Between B and C, it will be 2 on square times pi over 4. And between C and D, we have 1 on square times pi over 4, which will give me 0.25 pi inch square. So elongation here will be, since that we have a different cross-sectional areas, sum of all forces times length over area times modulus of elasticity. And in the segment AB, we have a force 6 kips times length, which is 50 inch. We are dividing that with the area AAB and times modulus of elasticity. Then we have a segment BC. For a segment BC, we have 6 kips force. Then we have 2 times 2 kips, which will give us 4 kips here. And at the end, we will have a force of 2 kips, which will be again positive. So that is 2 times 0.75 inch over pi times 18,000 ksi. And at the end, between C and D, we have pushing force, which is 1 kips, and that means -1 times 60's length. Then we have 0.25 times pi times 18,000, and in the end your answer will be 0.766 times 10 on -3 inch. Here I just noticed that on the figure B and C it is given kilonewton. That is a mistake. It's not kilonewton, it is kips. So we have 6 kips, 2 kips, 2 forces of 2 kips, and at the end we have between B and C 2 kips. And for the segment CD, again we have only 1 kip, which is a pushing. That means we have -1 kip. So this is one example for axial loading. Take care about St Venant's principle, and next time I will cover what we can do if we have some gap, how to determine the unknowns for statically indeterminate system. So you know that using the equation of equilibrium, we are not capable to solve the undeterminate system, which means you have more unknowns than equations of equilibrium. So what we will do in that case, check on the next video, and thank you for your attention.